All right. First, I'd like to thank the organizers for having me, and also thank everybody who's given talks, and I guess who will give talks. Everything's been really excellent, and I've learned a lot because I'm actually, I guess, what I would consider a card-carrying quantum chemist, and so I don't think about resonance states that often, and I also don't think about electron attachment processes, actually. So I do ground state theory, so I'm going to be kind of going on a trip away from what most of the people here have been talking about, but I think there's some interesting overlap. So I'm going to try and motivate this a little bit, both from the chemistry side and from the physics side. I'll talk just briefly about the theory because I think there are people in the room who are experts, and we'll kind of go through that quickly. And then I'll show some model systems that are kind of like very, very toy models that show some of the characteristics of these methods, and sort of maybe show at least some further reaches about their use. And then I'll just try and conclude and wrap up with sort of where we're headed with this. All right. Oh, and then I guess I should say that I'm from Martin Head Gordon's group as well, so that's where I come from. All right. So to motivate all of this, I think the first place that I like to start is with spin problems, and I mean that in two general ways. So the first one that I'd like to talk about is what is labeled in quantum chemistry as spin frustration. So in this case, it's where you have a spin state that's degenerate with another one. So in this case, I have an upspin, and a downspin. And I could choose these in essentially any pattern, right? And those would be degenerate states. So this leads to problems for a number of R methods that are approximate. So if you do full CI, probably not a big deal, right? You can just include all the configurations. But for approximate methods, this can lead to difficulties. The second thing, which is maybe more chemistry related and less related to physics, is that there's this choice of multiplicity. So for the people in the audience that know about it, Anna mentioned it briefly, there's this symmetry breaking problem, which is all I'm going to be talking about today. But specifically, people have to choose a multiplicity when they run standard quantum chemistry codes. So if you're running a transition metal, such as manganese 2+, there are a lot of possible spin states. So I could choose one where I have a quintet here, or I could choose one where I have a doublet. And the difference between these two is usually due to the ligand field, but that also has problems with geometry, right? So I can go between octahedral and a tetrahedral state, preserving spin, but losing two ligands. A normal quantum chemistry code would not allow you to do this transition. So you wouldn't be allowed to do a tetrahedral upspin to a square planar, even though the geometry changes there aren't so great. So this can be sort of a problem as far as potential energy surfaces go. And just to give a relevant chemical example, this is the oxygen evolving complex of photosystem 2, sort of a model of it. And you'll notice in purple here, these are manganeses, and the red here is oxygen. So you have a complex structure here where you don't really know exactly what the geometry is, and this doesn't fit into any point group symmetry, so I can't use this ligand field model to figure out what spin state I should be choosing, and there's also coupling between these metals. So if you want to tackle something like this, typically what's done is you run every single multiplicity you can think of and choose the lowest energy one and assume that that's the right one. This leads to sort of a lot of calculations and also biasing, right? If the geometry shifts here sometimes very small amounts, you can shift which spin state would be lowest in energy. And you won't be able to pick that up in a potential energy surface that doesn't account for that spin flipping. All right. So secondly, the thing that maybe interests me more and is probably more aligned with this audience are potential energy surfaces. So we'll get into that a little bit. But we want smooth potential energy surfaces if we're going to be running dynamics, very simple dynamics from different things that I've heard here. But overall, potential energy surfaces are interesting to physicists and chemists. And then because I'm doing Hartree-Fock, this is sort of another way to get at correlated methods. So we like to have a good reference state. Anna just mentioned it briefly, that they needed to use a complex scaled Hartree-Fock, or at least that was one approach they're going to be taking. That's a different reference state. I'm not talking about complex scaled Hartree-Fock. This is actually complex Hartree-Fock, and I'll make the distinction in a little bit. But this is our basis for all our correlated methods. So at least within the quantum chemistry community, we'd like to have a good reference state so that we can do correlation on top of it and get good energies. All right. So Hartree-Fock, I'm not going to go through this in detail. This is sort of a simple slide that I put together just to make sure everybody's up to speed. So it's a mean field solution to the Schrodinger equation. It's variational in that the energy is an upper bound to the exact energy. In this case, we're doing the Born-Oppenheimer approximation. So we have clamped nuclei. And it's just an anodized symmetrized product of single particle spin orbitals, so labeled as a Slater determinant. I've shown that here as sort of, this is kind of the schematic ket of that. And really what I'm going to be talking about today is really the structure of what one of these spin orbitals looks like. So this is what one of our molecular orbitals look like. So overall, what we do is we sort of pair up a spatial portion of the wave function represented by this psi j, which is a function of r, with a spin function. Here I've denoted it as sigma of Cassi. And that psi j, we expand it in a basis. So this is just my basis set expansion. We do atomic orbital-centered Gaussians, but whatever. And there's two types of constraints that are typically done in Hartree-Fock theory. The first one is sort of a spatial slash spin one, which will make sense in a second. And the second one is to restrict the wave function to be real. And we're going to break both of these constraints today. And so removal of these constraints is actually equivalent to breaking symmetry. In the 70s, all the states, essentially all the given symmetries that you can get for Hartree-Fock were classified by a professor in Japan named Fukutomi. And he went through and did like a rigorous group theory organization and classification of all the different states. And so that's been known for a long time, but I don't believe overall that this space has been explored properly, especially within the quantum chemistry community. All right, so this is a sort of famous quote from quantum chemistry by Lobdeen, where he says that there's a certain symmetry dilemma, which is what I'm talking about in the Hartree-Fock scheme based upon a single Slater determinant. If you look for the absolute minimum of the energy, it's a variational method, so that sounds good. Let's do that. You lose the symmetry properties, and by that he means the symmetry properties of full configuration interaction or the exact wave function within the Born-Oppenheimer approximation and so forth. And so if you look for those, the energy goes up considerably. So we kind of want to get both of these, but we can't. So we have to choose. All right, so what are we going to choose? Well, let's break some of those symmetries. So the first one that I said was that our wave function can be complex. And in this case, what I mean is just that the spatial portion of the wave function is broken into two components, a real and a complex portion. This is not the same as Anna's scaling or the complex scaling regime in general, where you're scaling the Hamiltonian. I still have a Hermitian Hamiltonian. There's no non-Hermitian non-Hermitian solutions going on here. And you could do this with complex basis functions, which was just mentioned briefly in the context of someone working in the group, in Martin's group, with Bill McCurdy, is planning on doing complex basis functions. The other way to do this is to use complex expansion coefficients. And so that's what this looks like if you use that. And that's the way that I did it due to the fact, as previously stated, complex basis functions increase the complexity of calculating the AO integrals. So calculating those integrals is more expensive. And right now, QChem has a very good integral code. So to take advantage of that, we just make the expansion coefficients complex. As a note, these in the complete basis set limit are the same, right? So I can either do the coefficients or I can do the basis functions, but at a truncated space, they're different. So that's just something to sort of a technical note. All right, so this is kind of a easy to go through slide overall. So there's three choices we can make in this spatial spin component that I mentioned before. And those three choices are, so at least we start out with a restricted case where we doubly occupy our molecular orbitals. And this is the sort of standard and was, was used for a long time. And then this theory can be extended to open shell systems by doing two spaces. So you do a doubly occupied space and a singly occupied space, so-called restricted open shell Hartree-Fock. Good things about this method are that we're an eigenfunction of total spin squared and an eigenfunction of our chosen spin vector SZ. So systems this describes are simple closed-cell systems. So your alkanes, your benzene, what have you, standard chemistry, I guess, or what we, I guess, think of as standard chemistry. We can do unrestricted, which probably most people in here are familiar with. This allows you to do open shell systems. So you have a spatial component that's different for the alpha space than it is for the beta space. This doubles the complexity of the problem, but that's not a big deal. And overall, this allows you to treat open shell systems. The problem here is that we end up not being an eigenfunction of S squared. So this was the spin contamination problem that Anna mentioned briefly. That seems like a big deal, I think, probably to this community to not be an eigenfunction of S squared. But to the quantum chemistry community, people do this all the time. So this is probably used 95% of the time, if not more. So what did we want to do? We wanted to go to something a little bit more exotic. And what we did is we did a generalized version of this. So this has been known for this since the 70s and was actually done earlier by Lobdeen, but only on some simple systems and at a semi-empirical level. So we want to take this on to correlated methods, so beyond that treatment. And what do I mean by generalized code? What that means is that you have every electron here, just chi I rather, is an alpha portion and a beta portion associated with the spin component. So it's a linear combination of alpha and beta. So this intrinsically should lead you to the picture that I described about flipping spins. You can smoothly move one molecular orbital between being fully alpha to fully beta. So this takes care of that multiplicity problem. The problems that it has are, once again, you're still not an eigenfunction of s squared, of course. And then you're also not an eigenfunction of sz. So in the real case, what this actually results in is that your spin vector can rotate into the x plane. So you get both x and z components to your spin vector. So that's kind of not a good thing. But systems that this can treat are the spin-frustrated systems. So systems where you have many metals, or in that case that I showed of the equilateral triangle, what ends up happening is the spins all point away from each other. So you end up lowering the energy, so this is a good thing, but you end up losing all these symmetry properties, a bad thing. All right, so what are we going to do with this? Well, let's start out looking at one of the complex restricted Hartree-Fock example. And I didn't mention, but I should have on the previous slide, that complex spatial component can clearly be used in all three of the spin/spatial ones. So I'm going to show a complex restricted solution, but you could go and do complex generalized, complex unrestricted, and so forth. I will note initially that I have yet to find a complex generalized solution other than possibly we think we have one in chromium-4. I'm not going to show chromium-4 due to the fact that we don't fully understand what's going on there. I don't think anyone ever has before known what's going on in chromium dimer, let alone 4 chromiums. So let's look at some simple examples instead of in that incredibly complicated case. So what I've done here is I've taken cyclobutadiene, a pretty simple molecule, and what we've done is we start at kind of this smush geometry, and we move it through a square geometry, and then we go to the other side of that. So this is a symmetric distortion where we keep all we're doing is adjusting this angle parameter, which kind of lengthens these bonds and shortens these bonds. Here I've exaggerated these angles, of course. Okay, so let's look at what that looks like. In the restricted real Hartree-Fock case, if we start out here at 40 degrees and we move towards 45 degrees, the square geometry, we end up having what looks like a cusp in the curve. But actually, if you take those molecular orbitals and you just try and follow them, so you stay on the same solution, you actually go up to infinity. So this is problematic from 2 reasons. 1, we don't really like cusps in potential energy surfaces. And 2, this method isn't obeying the symmetry of the molecule, right? So here I've moved between one side of the symmetry point and another side of the symmetry point. But my molecular orbitals don't show that at all. So that's very problematic. And so what happens if we allow for complex molecular orbitals? Actually, what happens is we have a mixing of what is the px and py in this case to the true p plus and p minus, and that allows us to break that symmetry and kind of go through that point, and we actually have a smooth curve here. So as we move through that, we get sort of a smooth connection between those two. So that's respecting the symmetry of this molecule, which I think is a very important thing if you're doing potential energy surfaces. Now this, to be fair, is also taken care of by doing unrestriction. So in this particular case, this is really just me trying to show a toy example of where this might be useful. This actually also appears in a lot of biradical systems where you end up having things where you want to mix into complex molecular orbitals. And that's one thing we're looking at is potentially looking at singlet triplet gaps for biradicals using these methods. And you might be asking how I found these solutions. And just to kind of show that, all I did was computed the eigenvalues of the second derivative matrix, so the Hessian here, or the second partial derivative really. And what you can do is you compute those and you can follow them in space here. So I've gone from 40 to 45. And you can see here, the ones that are blue you can actually block diagonalize this. And so if I do the block diagonalization from RHF, from the real RHF into the real RHF space, I get these blue eigenvalues. So you can see that it never becomes unstable with respect to restricted. But if you do the block eigenvalue problem towards the complex space, you see that here at this kind of fine point right here, you end up having a 0 eigenvalue, and you can follow that to the lower solution. So that's just how I find these solutions. All right. So going on to another kind of toy, I mean, these are all toy examples, but another toy example. If we want to find a real generalized Hartree-Fock solution, one simple example we can choose is this sheet of hydrogens. So this is a square lattice of hydrogens, 1.4 angstroms apart, and this is kind of like a Hubbard model in some ways, if people are more familiar with that, in sort of the weak regime. But if we want to pair these up and we kind of choose spins, because I've chosen 21 of them, they have to be sort of spin paired in one way. So we can either have an excess of beta or an excess of alpha, and that gets us these two configurations. And what we're going to do here is we're going to put a hydrogen on top of this hydrogen by 1.4 angstroms. So he's now coming out of the plane towards you. And we're going to move it along this sheet here. All right? And so if we start, let's say, with this configuration, which is the one that I'm going to choose to use for this example, and we start with an alpha hydrogen, right? Alpha spin rather than alpha hydrogen. That alpha spins are going to repel each other, so we're going to have a repulsion. And then as we move over the beta, they're going to attract, and we're going to have a repulsion again. So, repulsion, attraction, repulsion, attraction. If we start with the other spin, we'd end up having the opposite effect. So what do those curves look like? They look like this. So if I do unrestricted here, restricted Hartree-Fock will give you garbage, so let's not even consider that, of course. So the unrestricted case, though, we have this oscillation, which is interesting, but also unphysical. It doesn't have the periodicity of the system, right? We're moving between spins here, and these kind of look like what you might think of as adiabats in some sense. So that's good. So what is, if we go to the generalized case, what does that look like? So I'm just going to focus in on this portion of the graph here. So if we look at the generalized case, which I've done in green here, you can see that it moves between these two curves, and if we zoom in, it actually smoothly moves between these two curves. And all that it's doing there is, as we go along this thing, it's taking one of our spins and moving it out of the Z plane, not out of the Z plane, sorry, away from Z towards X, and then back to Z again. So it becomes from alpha to beta, alpha to beta, alpha to beta as we go along. All right? So that's sort of one application of this, admittedly a very toy and simple one, but it shows some interesting physics. What we'd like to do with this is kind of extend this and see how far we can push it. Can we take and do, instead of simple hydrogen single spin systems, do multi-spin systems? So something like oxygens moving over oxygen. See how many spins it can flip. See what this gets us back. And I think this is interesting from another perspective in the fact that a lot of times when we talk about correlation, we separate ourselves, at least within the quantum chemistry community, to focusing on correlation that's involved from a restricted Hartree-Fock level. But I think there's a lot of correlation that's also a spin type correlation that we don't typically think about. So I just think opening up some possibilities there. And I'd like to mention that this isn't necessarily what the actual physical system is doing, right? So there's a lot more going on. We have spin coupling that's happening, and there's spin orbit coupling that I'm clearly not taking into account at the Hartree-Fock level. So this isn't necessarily trying to look at what the actual physics of this system would look like, but more trying to look at what my model chemistry is doing for me. All right, past that. So another system that we've talked about today quite extensively, and I'd like to briefly touch on at a much simpler level. I didn't do CAS-SCF on oxygen at all. I'm just doing Hartree-Fock. But if we think about oxygen, we have a triplet state, at the equilibrium position. And we also have triplets, at dissociation. So there's a problem there, in that if we do, I mentioned briefly that in unrestricted we have to choose a multiplicity. So I'm going to ask you to choose the multiplicity of our two triplets, and we can either choose a singlet out here at dissociation, or we can choose a quintet to get the minimum energy. If I try and bring either of those pairs together, there's no way for unrestricted Hartree-Fock to get that right. So unrestricted Hartree-Fock, at the Hartree-Fock level, we can't dissociate oxygen. This seems like a big problem, but if we allow some of those spins to flip, it's good. So here I'm showing that at equilibrium, we have a pretty decent potential energy surface, clearly Hartree-Fock level, so don't run dynamics on these curves or anything, especially this unphysical hump here. But neither here nor there. So if we take the triplet UHF solution out to equilibrium, we end up with this totally unphysical dissociation, right? We're well above 2 triplet oxygens. If we take the singlet in from dissociation, or start here, it doesn't matter, we end up dissociating to the correct limit, but we're terrible at equilibrium. So what does GHF get us? It gets us this smooth curve in between, and if we look at this finite region in here, it smoothly connects those two curves. All right, so this was just a brief overview of some toy systems that I'm looking at, and I really would like to say that as far as complex generalized Hartree-Fock goes, I don't think that, at least within our community, this isn't fully understood when we need to apply it. So what I'm currently working on is figuring out when we should think about applying this and what it actually means. I mentioned briefly that H kind of cannonball system, we're not really describing what the actual true physics are. We're describing what our model physics are doing wrong, which is maybe not necessarily interesting if you want to think about this from a perspective of applying it to actual experiments, but from my perspective, looking for failings in methods that people do every day is quite good. And so I've shown you some, I've sort of briefly described the theory, shown you some model systems, and as I just said, we're still developing our intuition for when these things are going to be applied. I think one of the greatest uses, which is maybe more chemistry oriented, is the fact that you don't have to choose a multiplicity. So I think one thing that people do semi-frequently, so I got interested in this because of the transition metal problem. I worked primarily in transition metals when I first started in Martin's group, and it's a real pain to go through and do all the multiplicities, and you still don't really know what you get at the end of the day. So I think that's sort of one thrust. Another thing that we can do with this is we can also do cone-sham density functional theory. The same classification scheme holds for the one particle density matrix, so you can do cone-sham density functional theory on top of this, on top of cone-sham orbitals of these types. There's a little bit of weirdness there in that you kind of get a cross-density term that looks like an alpha/beta density, and how to actually handle that within a cone-sham formalism isn't very well known. And to top it off, all our current codes are, well, at least within chemistry, are usually optimized over some set of molecules, and those are always optimized at an unrestricted level. So all the parameters that are involved are for unrestricted cases. It's well known. Actually, Becky did a complex functional at one point because he found that in one of his data sets he was finding atomization energies that were unstable with respect to complex orbitals. So he actually wrote up a real quick complex density functional theory as well. So it's known that unrestriction doesn't necessarily get you everything that you want. Other areas that I'm looking at are post-Hartree-Fock codes, potentially linking into some of Anna's couple cluster work. You could do couple cluster on top of this. You can do MP2. You can do sort of all the standard gamut of things that we know about doing. And then something a little bit different, which I think maybe relates a little bit more to this community and is maybe an interesting point that was made earlier, is one thing that I'm looking at doing, which has already been done for restricted and unrestricted Hartree-Fock within QChem, within my group, is this non-orthogonal configuration interaction. So we actually have ways in our group to find multiple solutions to the SEF equations using a metadynamics approach. You can also find them using this Hessian approach that I showed before. That second partial derivative, when it hits 0, you could also follow the positive eigenvalues to new solutions as well. So there's no need to go down in energy. You can also go back up. So if you find multiple configurations, you have different Slater determinants, you can interact them just like in configuration interaction. Typically what's done in configuration interaction is that the states that you're interacting are orthogonal. In this case, Slater determinants are not. So you have to do a non-orthogonal theory. And one of the reasons that I'm looking at this with relation to this set of sort of thoughts about sort of broken symmetry solutions is that what we're looking at here is we're looking at a denser manifold of states. So if you want to think about what states you can find in a restricted case, you can only find double excitation-esque things, right? SEF solutions that look roughly like double excitations. In unrestriction, you can find ones that look like single excitations. In generalized one, you can find ones that look like excitations, where I don't really know what those excitations look like because they're partial spins of different types. So doing that means that we have a denser manifold of states, which means maybe we need to include less of those states to get a lower variational energy, at least for our ground state. All right, and with that, I'd like to thank my boss, Martin, postdoc in the group who's been very helpful, David Small, the whole of the Head Gordon group and the DOE for funding, and you for your attention. Thank you.
Questions? You've shown to us that when you use a complex basis function, you get a volume crossing, but if you use real basis functions, then you've got a crossing between the two potential surfaces.
Yeah.
Is it possible that they are somehow related, because of the examples that you have shown, to representation of conical intersection by adiabatic solutions? This you get adiabatic potential surface when you use complex basis functions, and you use the real basis function to get the diabatic potential surfaces, which actually it's better to use them in the computations because then you avoid to introduce the coupling beyond the Born-Oppenheimer in the kinetic potentials, but now you have it in the diabatic representation.
Yeah. Yeah, so I think there's a lot of relationships to that actually kind of all over in this work. I think one of the things that was done not necessarily at this level, but at the non-orthogonal CI levels, looking at conical intersections themselves. And I think there is a relationship between adiabats and diabats in this sort of spin or complex, as the case you're describing, picture, and what people do in like nuclear geometry, where they have the.
If this is so, it's actually, there is an advantage.
There's an advantage to using. Yeah, I agree with you on that. So I mean, I'm not claiming that this is sort of the end of the picture there. Yeah. So yeah, essentially. Yeah.
Yeah, I also have kind of a naive question of a real Schrodinger equation if you have no spin orbit terms in Hamiltonian, so there exist real solutions. So I don't quite understand what you think will happen with complex basis functions.
So I think in answer to that, I think within the approximation, you're reaching a point when it gives you more variational flexibility. So if you're at a finite basis, right, allowing for the complex set can give you more variational flexibility. So it's not necessarily that you end up with, in the full CI limit, you wouldn't have a complex, you wouldn't have any need of this, right? Yeah.
Just to comment on this, so maybe this is obvious. It's true of all these symmetry breaking solutions. You have a single determinant in terms of these complex orbitals. If you expand this now in terms of the real orbitals, you have a multi-configurational wave function.
Yeah.
So this is a way of picking up correlation effects within a single determinant.
Yeah. So it's not necessarily that we actually, I guess, in the full CI limit, we wouldn't need this ever, but that's true of, I guess, many things. Mm-hmm.
Because related to this complex basis function, you didn't mention it, but I think that I know when you mentioned that Bill McKelvey wants a new group to use the complex basis function.
Mm-hmm.
And I assume that the motivation is different. Instead of using real basis function in complex scale operators, you can take the original operators, original Hamiltonian, and to scale the basis functions.
Yeah.
You don't complex conjugate.
Yes, exactly. You don't take the complex conjugate. This is the point. Now, if you scale all your basis functions, this is equivalent. But if you scale only the most diffuse orbitals, or the orbitals like Anna spoke about, then actually it's not really equivalent. And the motivation is to say, maybe this way they can go to large systems, even molecular system, and then to use complex basis function without taking the complex conjugate.
Yeah, I think their motivation, I mean, the connection between my work and Martin's collaboration with Bill McCurdy is non-existent in a sense. Like we're not talking at all yet. So I think I did mention it. So I want to clarify that you know his approach to doing the complex basis functions. One, we just got a new grad student who's going to be doing that. So that hasn't even started. And so I think to a certain extent, that wasn't a viable option for me earlier on. So.
Any other questions? Well, let's thank the speaker and